Today I'm gonna talk what the upper atmosphere can tell us about tomorrow's forecast. Have you ever wondered how weather forecasters know what the weather will be tomorrow? It all starts from numerical weather prediction. This model divides Earth's atmosphere into three-dimensional grids. In each grid, it takes as an input the measurement of different atmospheric variables, such as the temperature, humidity, pressure, wind speed. And then, by using numerical equation, you know to solve the equation and give us as an output what this variable will be in the next time step, so in the next hour, in the next day, or even in the next week. These predictions help us to make decision-making, such as what we are going to wear tomorrow, or more important decisions such which road in the Negev should be closed. In my research, I am examining the reliability of this weather prediction, focusing on Mediterranean cyclones. This type of weather system, the Mediterranean cyclones, can cause high-impact weather, such as high waves, flash lightning, strong winds that can cause damages, dusty winds, and even floods. Moreover, this type of cyclone can contribute a large fraction of the annual precipitation. Actually, more than 90% of the annual precipitation, the annual rain in Israel, is associated to this type of cyclones. But a Mediterranean cyclone may look like it's formed near the surface, but much of its behavior is controlled from above. You can imagine it as a puppet and a puppeteer. When the upper level part of the atmosphere is a puppeteer that controls a puppet, which is in our analogy, a cyclone. And by that, it can shape its path, intensity, or even the amount of rain that produced. But these cyclones have large case-to-case variability. So here in this cloud pattern, you can see different cyclones that occur above Israel, and you can see the large variability from these images. Therefore, in my research, I have classified all the Eastern Mediterranean cyclones with respect to their upper level behavior, the puppeteer behavior. So I took all these cyclones from 1979 to 2020, and I took only the ones that entered the Eastern Mediterranean domain. And I got 686 cyclones like that. For each of these cyclones, I looked at the time that correspond to the most intense time of the cyclone. And now I'm looking above on the puppeteer behavior. So for each of these cyclones, we have different puppeteer behavior. And now I have almost 700 puppeteer behavior, and I want to classify them. So for that, I'm using self-organized map. So, which divide this cyclone in respect to the puppeteer behavior into 6 types. This study helps us to understand the connection between this puppeteer behavior to the actual impact of the cyclones. So here you can see the puppeteer behavior of the cyclones, and for each of them, we have a distinct type of impact. So for example, if I'm looking on cluster number 1, with a specific puppeteer behavior, we saw that this kind of cyclone correspond to strong precipitation and cold anomalies. And other cyclones from cluster number 5 is actually correspond for warm anomalies and have low amount of precipitation. But forecasting these cyclones is still a challenge, especially if you are talking several days in advance. Forecasts often predict, for example, the right location, but the wrong amount, or the opposite way around. So forecast is not just right or wrong. It's much complicated than that. For high-impact weather, we must ask, is the location of the feature that we was forecasted in the right location? Is the intensity was correct? Is the shape of the feature was forecasted well or not? But the traditional scores, such as root mean square error, miss this key aspect of the forecast quality. Therefore, in my research, we use the SAL method, which knows to quantify the structure of the forecast, the amplitude of the forecast, and the location of it. So maybe now it's complicated, but I will explain. So the main question, are there specific weather pattern, perpetual behavior, that make Mediterranean cyclones forecast better or not? So here I'm showing you an example from a cyclone that occurred just before the first COVID lockdown. And these cyclones caused the devastation of more than 75 of the coral reef in Eilat. And you can see in this image, the satellite image of the cloud pattern, but also you can see the actual precipitation observation. And in this panel, you can see what we have forecasted just 48 hours before the event. But imagine yourself living in this area. You look on the forecast just 48 hours before the event, and during the event, you get twice the amount of the precipitation than you expected from the forecast. So for each of these precipitation features, I define an object. And now I can see, for this object, I can quantify how the structure of the object of the observation against the forecast was accurate, how the location of the center of the mass of this feature was forecasted, and also the amount of the precipitation inside this feature. So now, in this tree panel, you can see in the x-axis the lead times, so the hours before the event. In the Y panel, you can see the different cluster, which is the different perpetual behavior. And in color, you can see how good or how bad we forecast them in different times. So first, we can see that as the lead time getting shorter, we are approaching the actual event, the forecast getting better, especially in location and amplitude. Moreover, for example, if we look on specific cluster, we can see that, for example, in cluster number 5, the intensity was predicted more or less good, but if you look on the structure of the feature, the prediction wasn't so good. Another example from cluster number 2, here we can see that both the amplitude and the location was predicted relatively good, but again, it's failed to predict the structure. And we can see that we can quantify also the perpetual behavior, and also we know that the model versions that I talked in the beginning of my presentation, the numerical weather prediction, have updated versions from time to time. So in this research, I can also see, for example, for the location score of the precipitation, how different model version in the y-axis behave. So we can see that some versions are better than others. And some are, for example, from version CY41L2 is less good. So what did we learn? So the model cannot predict the events perfectly, especially when we are talking several days in advance. For example, for some upper atmosphere patterns, it predicts the storm strength well, but failed to predict the location and structure. And in general, simple quantification methods such as root mean square error suggest improvement closer to the event. But more detailed methods, such as the SAL method that I showed you, tell a more complex story about the forecast. So the upper level atmospheric pattern, the puppeteer behavior, will determine how well we can forecast the weather in the upcoming days. So next time you are looking on the weather app, just remember, it's all controlled from above. Thank you for listening, and thank you for the gift.